In this video, I'll be discussing Hardy-Weinberg Equilibrium and how it is affected by selection within a population. We will be observing how this happens by using a population of fairies with different wing sizes. In a population of 87 fairies, there are 3 different phenotypes: normal wings, small wings, and no wings. Of the 87, 53 are homozygous dominant and have normal wings, 29 are heterozygous and have small wings, and 5 are homozygous recessive and have no wings. These are the genotype and allele frequencies and the calculations that were used to get them. Hardy-Weinberg Equilibrium is a model that addresses allele and genotype frequencies in a population. When a population is in HW equilibrium, the frequencies follow the equation p squared plus 2pq plus q squared equals 1, where p is the frequency of the dominant allele and q is the frequency of the recessive allele. To demonstrate that this population is in equilibrium, we will use a chi-squared test. Our null hypothesis is that this population is in Hardy-Weinberg equilibrium. Our observed values are already in the chart, and to find our expected values, we have to use the equation. As shown before, our p-value is 0.77585 and our q-value is 0.22415. The expected frequency of big A is p squared, which is 0.60196. The frequency of big A is 2pq, which is 0.34780. And the frequency of little a is q squared, which is 0.05024. Multiplying these values by the total number in the population gives you the expected number for each, which turns out to be 52.37, 30.26, and 4.37 respectively. To fill out the rest of the chi-squared chart, we do observed minus expected squared divided by expected for each class. The sum of these numbers is our chi-squared value, which is 0.1505. There is 1 degree of freedom, which was found by subtracting the number of alleles from the number of genotypes. The critical value for 1 degree of freedom is 3.84, and our chi-squared value is less than this number, so we fail to reject the null hypothesis. Now that we know that our population is in Hardy-Weinberg equilibrium, let's see how it is affected by selection. In this species, having wings allows them to escape their main predators. The normal winged ones have the highest fitness at 1, small winged ones have a lower fitness at 0.8, and the wingless ones have a fitness of 0.5. To find the survivors of selection, we multiply the initial frequency by the fitness for each genotype. The sum of those numbers is the average fitness in the population, or how many of the original population survived. To find the frequency of the genotype after selection, you divide the survivor frequency from each genotype by the average fitness. The genotypic array for the new population is 0.6734 big A, 0.2948 big A, and 0.0318 a. Now we will use the new genotype frequencies to calculate the allele frequencies after selection. For big A, we take the frequency of big A and 1/2 the frequency of big A, which is 0.8208. For the frequency of little a, just subtract the frequency of big A from 1, which is 0.1792. By observing the chart, you can see that the frequency of the normal winged phenotype has increased and the other two have decreased. When the frequency of phenotype shifts towards one extreme, it is known as directional selection. If directional selection continues to occur in this population, eventually all of the species will be the favored phenotype, so in this case, they will all have wings.